In this video, we're going to talk about systems of linear equations in two variables. Now, a system of equations is just more than one equation at the same time. A system of linear equations just means that both of the equations are going to be linear, meaning they make straight lines when you graph them. So, in order to find a solution for a system, you need to find any points that satisfy both of the equations at the exact same time. There's only three possibilities for how two straight lines can be graphed on the plane. One possibility, if you graph two linear equations, is that the two lines will intersect each other somewhere. Something like this. Obviously, yes, there's a lot of different ways for the lines to intersect, but it's possible that they hit each other like this. If you have one intersection like this, this means that there is one solution to that system of equations, and it's the point where they hit each other. Another possibility, if you graph two lines on the same plane, is that they never hit each other. They're parallel. So here's an example of parallel lines. They don't hit each other ever. This would be a system that has no solution, because the solutions are where the two lines will intersect each other. And then the third possibility is if you were to graph the two linear equations, the graphs of the equations end up representing the same exact line. So here's one of the equations, and if you graph the other one, it lands directly on top of the first one. They're the same exact line. In this case, you would have infinitely many solutions. When you have no solution to the problem, like over here, we say that this system is inconsistent. And when you have infinitely many solutions, the system is dependent. So there are two main ways that are generally taught for how to solve a system with two linear equations. One of them is called substitution. The other one is called either elimination or the addition method, depending on what your book uses, but it's the same thing. Substitution tends to be very popular with students when they're learning this material because it's a little easier to understand at first. I personally am a big fan of elimination. I will present both ways, and I tend to pick and choose depending on the particular problem, but we'll learn how to solve these systems with both of those methods in this particular video. We'll start with substitution. So to solve a system of linear equations in two variables with substitution, the first thing you want to do is isolate one of the variables. So what I mean by that is you're going to choose one of your equations and solve it for a variable of your choice. It does not matter what variable you solve for. Then you're going to substitute that value into the other equation. So substitute the result from one into the other equation. Step 3, solve this new equation. And then the last step, substitute your result from 3 back into the result from 1. Since our solution is going to be a point where the two lines hit each other, you're going to have one answer for x and one answer for y. and the solution is the ordered pair x, y. So let's do an example. We are going to solve the system of equations 3x plus 4y equals 5, x minus 3y equals 6. So I have two equations here, and I'm looking for all the places that these two equations agree. So I want all of the points that satisfy both equations at the same time. And we're going to use substitution. So again, it does not matter which equation we start with. Choose the one that looks easier. I personally would choose the bottom equation and solve it for x, because I can do that with just one step. So let me take this x minus 3y equals 6 and solve it for x. And I will get x equals 3y plus 6. Now I have to take this information and plug it into the other equation. So I had 3x plus 4y equals 5. Now I take the information I just found out and plug it into the equation. So 3 times x will now be 3 times 3y plus 6. I can now solve this for y. Distribute. So when I distribute, I get 9y plus 18 plus 4y equals 5. Combine my like terms. Subtract 18 and divide by 13. And I get y equals -1. And that's part of my solution. But now I still have to figure out what x is. So I get to take this result and plug it back into the equation I had that had x by itself. I had x equals 3y plus 6. So now I can plug this y value in and get that x is equal to 3. So the final answer to this system of equations is the point 3, -1. If you were to graph those two equations, they're going to hit each other at that point. So now we've solved our first system of equations using the method of substitution. Now what about this other method, this elimination or addition method? The first step for this method is to write the equations in standard form. So that's ax plus by equals c form. Step 2, which is optional, but I highly recommend, is to clear all of the fractions or decimals, just so that you have nice whole numbers to work with. Step 3, multiply one or both equations by a non-zero constant to create opposite coefficients for one of the variables. So this is the most complicated step in the elimination or addition method. What the goal is either for the x's or for the y's, you want the coefficients in the two equations to be opposites of each other. So if I have a positive 4 as the coefficient of x in one equation, I want the coefficient of x to be negative 4 in the other equation. You want them to be opposites. The reason for that is because step 4 is to add the two equations together. So if you've made it so that the coefficient on one of your variables is opposite in the two equations, when you add the two equations together, that variable is going to completely disappear. Step 5 is to solve this new equation that you get. And step 6 is to substitute back into either of the original equations. Now, elimination or the addition method sounds very complicated and has a lot of steps, but I personally feel like it goes quicker than substitution in a lot of problems. So let's do an example where we use this method. I have 2x minus 9y equals 1, and 3x equals 17 minus 2y. Now, the first thing I need to do before I do anything else is to put both equations in standard form. My first equation's already good. I have 2x minus 9y equals 1, but my second equation I have to rearrange by adding 2y to both sides so that it's in standard form. 3x plus 2y equals 17. And now we have to make a choice. We can either try to eliminate the x's or try to eliminate the y's. And it's up to you which you do. I personally would eliminate the y's on this one because I already have opposite signs. I just don't have opposite coefficients yet. But you could multiply by things to get the x's to cancel out as well. But I personally would multiply my top equation by 2 and the bottom equation by 9. When I do this, this negative 9y will become negative 18y, and this 2y will become positive 18y. So they'll be opposites of each other. So let's rewrite what these equations look like after they're multiplied. I will have 4x minus 18y equals 2, and 27x plus 18y is equal to 153. So now I have opposite coefficients on my y. Now I get to do the step that eliminates my y variable, and we do that by adding the two equations together. So when I add my two equations, 4x plus 27x is 31x. My negative 18y plus 18y is 0. And 2 plus 153 is 155. And I can solve this equation by just dividing by 31, and I get x equals 5. Now all I have to do is find y. And to get y, I just take this value and plug it back into either equation. And I guess I'll plug it back into the first equation. My first equation was 2x minus 9y equals 1. When I plug the 5 in, I get a 10. So I'm going to add the 9y to the other side and subtract the 1. And I'm going to do that all in one step. So I'll end up with 9 equals 9y. And when I divide by 9, I get y equals 1. So my solution is the point 5, 1. And there's our first example all the way through of the elimination or addition method. Which method you happen to prefer, it's a personal thing. Like I said, I prefer elimination for most cases. Sometimes I'll use substitution, but usually I think elimination is faster. But if you personally really like one method over the other, just use the method that you like. It does not matter which way you do it, you'll get the same answer either way. Let's do another example. We're going to do one that gets some ugly answers. How about 2 times x minus 2y equals y plus 14, and 1/2 x plus 7/6y equals negative 13 over 3. Well, the first thing we have to do is get these into standard form, and I'm also going to get rid of all those fractions. So let's get the first equation into standard form first. I will distribute to get 2x minus 4y equals y plus 14. And it's almost in standard form now. I just have to subtract a y and I'll get there. So I will get 2x minus 5y equals 14. That's my first equation in standard form. Now for my second equation, it's already in standard form, but I just have nasty fractions everywhere. So if I want to rewrite this so it's not as ugly, we're going to want to get rid of the fractions. Let me first write down the new version of my first equation. Now let's take a look at the second equation. Look at all of the fractions that we have. I have a denominator of 2, 6, and 3. If I multiply everything in that equation by 6, I'll get rid of all of the fractions. So let's multiply everything by 6. Six times 1/2 is 3. 6 times 7/6 is 7. And then 6 times this negative 13 over 3 is negative 26. So that second equation here that had all those fractions, I can now write it as 3x plus 7y equals negative 26. All right, so now I have both equations in standard form and I have no more fractions. So now let's figure out how to do this, and I'm going to use elimination again. We want to get rid of either the x's or the y's, and like last time, I notice I have these opposite signs on my y, so I'm going to get rid of the y. I'll multiply the top equation by 7 and the bottom equation by 5. And that will make it so my y's have a negative 35 and a positive 35. So when I multiply the two equations by those numbers, I get 14x minus 35y is equal to 98. And I have 15x plus 35y is equal to negative 130. So now if I add the two equations together, my y's disappear, and I get 29x is equal to negative 94. When I divide both sides by 29, though, I don't get a nice number. I get x is equal to negative 32 over 29. It's not 94. Wow. This should be negative 32. I apologize. I was looking at a different number on my sheet. So let's talk that over since I messed that up a little bit. When I added the two equations together, 14x plus 15x is 29x. My 35y's go away, and 98 plus a negative 130 is negative 32. I solve for x by dividing both sides by 29 and get x equals negative 32 over 29. Now, at this point, this is where we took this value before and plugged it back into one of the original equations to solve for the other variable. But I don't know about you, but plugging in negative 32 over 29 into one of these equations just does not sound like a good time to me at all. So I'm going to show you a different way we can do this. Put a box around your x so you don't forget what that answer is. And go back to our system before we eliminated the y's. This time, if I instead eliminate the x's, I'll get an answer for the y value. So if I wanted to do this again with elimination, multiply both equations by a non-zero constant so that my x's get opposite, I would multiply the top equation by, well, I'll multiply the top one by negative 3 and the bottom one by 2. That will make this x term into negative 6x and this one into positive 6x. So when I multiply everything out, we get negative 6x plus 15y is equal to negative 42, and positive 6x plus 14y is equal to negative 52. And if I add those two equations together, we get 29y is equal to negative 94. And if I divide both sides by 29, I get y is equal to negative 94 over 29, which is an equally ugly number. So the answer to this system is the ordered pair negative 32 over 29, negative 94 over 29. It's a really ugly answer, but it's the answer that we get. So it's the correct answer. So this example here was to show you that if you get something really gross, you don't have to plug that back into an original to find the other value. You can just do elimination again to get the other variable instead. Let's do another couple examples, and then we'll move on to word problems using systems of equations. So let's solve 3x minus y equals 2, and negative 9x plus 3y equals 4. So again, I'm going to use elimination on this one. And the first thing I notice is that my y's are opposite sign, and if I multiply my top equation by 3, they'll have opposite coefficients. So let's multiply the top equation by 3. And I'll leave the bottom equation alone. That gets me 9x minus 3y equals 6, and negative 9x plus 3y equals 4. So now if I add the equations together, well, 9x and negative 9x is 0, negative 3y and 3y is 0, and 6 plus 4 is 10. So I get 0 equals 10. And does that mean we messed up? No. This just means there's no solution. So if you're solving the system of equations and get something that is just outright nonsense, like 0 equals 10, you have no solution. This would be one of those situations where if you graph the lines, you would have parallel lines. Well, how about the equations x equals 5 minus 3y and 2x plus 6y equals 10. Now, this problem I would actually use substitution on, and the only reason for that is because my top equation already has x solved for. So I can take the top equation and plug it into the bottom equation and get 2 times my x plus 6y equals 10. I plug the x in, 5 minus 3y. And now let's distribute. 10 minus 6y plus 6y equals 10. When I combine like terms, I get 10 is equal to 10. Now, what happens there? Well, this time all my variables are gone, but 10 equals 10 is a true statement. It's not nonsense like we had on the last problem. So when you're trying to solve and all the variables disappeared, but you get something that's true, this means there's infinitely many solutions. And then how do we write our solutions? Well, there's a lot of different ways to write it. I'll show you one way. We know that it's going to be the set of all points that satisfy our equations. So what do these points look like? Well, I know x is going to be equal to 5 minus 3y for whatever y is. So all of my points are going to be of the form 5 minus 3y and y, where y is a real number. So when you have a situation where you have infinitely many solutions, you want to write your ordered pairs kind of like this. You're going to have just take one of your equations and solve it for one of your variables. Put that info in for that place on the point, and then the other coordinate is just going to be that variable. So I have 5 minus 3y for my x, and just y for my y. All right, now we have to do 2 more examples, but they're word problems, so that should be a lot of fun. So here's an example. How many ounces of 20% acid solution and 35% acid solution should be mixed to produce 15 ounces of 30% acid solution? So this is a systems of equations problem, but we don't know what the system is yet. We have to write our own equations to make up the system by reading the word problem. First thing you need to do is define your variables. I'm going to let x equal the number of ounces of the 20% solution. And I'm going to let y equal the number of ounces of the 35% solution. Now, one of the equations that I know for sure is that x plus y has to equal 15 ounces. So I have one equation dealing with the total number of ounces. X plus y equals 15. But I also have to have an equation dealing with all of the percentages. My 20% solution is 0.2 times x. My 35% solution is 0.35 times y. and I want it to be a 30% solution, so that's 0.3 times my total ounces, 15. So my top equation is just talking about the number of ounces, and the bottom equation is talking about the amount of pure acid in all of these solutions. So the first thing that I would do on this is get rid of all of these decimals, and I can do that by multiplying the bottom equation by 100. My top equation is still x plus y equals 15. Now if I multiply my bottom equation by 100, I will get 20x plus 35y is equal to 450. And now I have a nice system to solve here. I'm going to solve it using elimination just because I happen to prefer elimination. And let's eliminate our x's. If I multiply the top equation by -20, that will get me x's of opposite signs. So my top equation now becomes -20x minus 20y is equal to 15 times -20, which is -300. And my bottom equation is still 20x plus 35y equals 450. Add the two equations together. The 20x's go away, and I get 15y equals 150. Divide by 15 to get y is 10. Now remember, one of my equations was x plus y equals 15. That's the easiest one to solve for x on. I would have x plus 10 is 15, so x is 5. Now all I have to do to answer the question fully is remember what x and y stand for. X was the number of ounces of the 20% solution. So I need to mix 5 ounces of the 20% solution and 10 ounces of the 35% solution. Now, even though we just figured out how much acid to mix together, please do not go mixing a bunch of acid together unless you're a chemist and actually know what you're doing when you're mixing these acids. All right, let's do one last word problem example, systems of equations in two variables. A boat takes 3 hours to go 24 miles upstream against the current. It can go downstream with the current a distance of 48 miles in the same time. Determine the speed of the boat in still water and the speed of the current. So these types of problems where you're talking about distances and speeds and time, you need to know the equation distance equals rate times time. That's what we're going to need to use in this problem. Distance equals rate times time. So I need to come up with some variables to use to represent the speed of the boat and the speed of the current, and then I need to set up some equations. So I'm going to let B equal the speed of the boat. And C equals speed of current. And I personally like making tables on these problems, but you don't have to. I'm going upstream or downstream. I have my distance, my rate, and my time. So according to all that info that the problem gave us, upstream, I can go a distance of 24 miles in 3 hours. And I know I can go downstream 48 miles in the same amount of time, so also 3 hours. The rate is the kind of tricky part, but we can figure it out. Going upstream means that the boat is going one direction and the current's going the other direction. They're pushing against each other. So the boat is going to be traveling overall at the speed of the boat minus the speed of the current. Because the boat's going one way and the current is pushing against it, slowing it down. Now, going downstream, my current is going this way. That means my boat is also going this way. So their speeds are going in the same direction. And so together, the speed is B plus C. So if they're going in opposite directions, you have to subtract the two speeds. And if they're going in the same direction, you add the two. Now I have everything I need to set up my system using distance equals rate times time. One of my equations is going to be my distance of 24 equals rate B minus C times time 3. And my other equation is distance 48 equals my rate B plus C times 3. And there's our system of equations. Now, your first instinct might be to distribute the 3's. I personally would just divide both equations by 3 to make my numbers smaller. You could distribute though, you would still get to the same exact answer. I'm going to divide though, because I like to make my numbers smaller whenever I can. So if I divide both of my equations by 3, I get 8 is B minus C, and I get 16 is B plus C. Now, this is already set up beautifully for the elimination or addition method, because notice I already have opposite coefficients on my C's. So let's go ahead and just add the two equations together and get 24 equals 2B. Which means B is 12. Then to find C, I just have to plug that into one of my equations. And it doesn't matter which one. So I'm going to use, well, let's use the bottom one. 16 equals 12 plus C. So that means C is equal to 4. Now, what does this mean? Well, B was talking about the speed of the boat. So the boat is going 12 miles per hour if there was no water pushing on it. And the current, the speed of the water, is going 4 miles per hour. And there we go. So now we can solve pretty complicated word problems just using our systems of equations. Now, in the next video, we're going to do more systems of equations, but instead of just having 2 equations and 2 variables, we're going to have 3 equations and 3 variables. So a lot of the ideas are the same, but it's amazing how adding one more variable makes things a little more complicated. So please come back for the next video to see how we handle an extra variable. If you have questions, drop them below, or you can come to office hours or email if you're one of my current students, and I'll see you for our next video.